These days, it's not surprising to see digital technology incorporated into the modern vehicle. A key part of this technology has been the use of pulse width modulation, or PWM. PWM is perfect as an input or output for a control module because it's digital. As an input, there's no need for an analog to digital converter. Now, we've all seen the effects of PWM control in electromechanical actuators. But do we really understand how it works? For an engine control module to operate an actuator, it first generates a command from the central processing unit. I'll be using this microprocessor to simulate a control module. These commands are in the form of a high or low control set against a time base. This on-off or digital control is pulse width modulation. Output drivers operate in response to the digital commands issued from the CPU. The output driver may be labelled as high or low side, depending if it's required to switch power or ground. In the past, you may have seen schematic representations of a driver look something like this. But in reality, it would look like this. The output driver is a transistor. It uses a small current to control the operation of a larger current path, much the same as an automotive relay, but with no moving parts. Let's look at some digital commands at the CPU with an oscilloscope. You can see a square wave pattern on the screen. The time base is set at 1 second per division. On this trace, the processor is pulling the circuit high for 1 second and then low for 1 second. This is 1 cycle. What we are seeing is a graphical representation of what the software has been programmed to do. The output driver is simply responding to the high and low commands, resulting in a PWM control. Duty cycle is a measurement of the amount of time the control is on or off, compared to the time of 1 complete cycle. It's expressed as a percentage. A positive duty cycle is held to ground and pulled high to activate, whereas a negative duty cycle is held high and pulled to ground to activate. This schematic shows a control module and solenoid. As you can see, the module houses a high side driver. The solenoid has a constant ground. When activated, a positive duty cycle control is sent to the solenoid. This PWM control has a duty cycle of 75%. It's pulled high for 3/4 of a second and then released. This solenoid is supplied with voltage on one side and is pulled to ground by the control module on the other. This trace has a negative duty cycle of 85%. The solenoid is pulled to ground for 850 milliseconds. If I was to measure this control with a multimeter set on duty cycle, the meter would default to a positive reading. Unfortunately, it would be incorrect. The meter would display 15%, whereas the correct reading should be 85% duty cycle. The meter only registers that the circuit has been pulled from ground to voltage. In reality, this is when the circuit is turned off. The on time is actually when the voltage is 0. If a circuit has a resistance fault, it may not be detected using a multimeter set on duty cycle. The excess resistance will not affect the duty cycle percentage, but it will affect the operation of an actuator. The current flow in the circuit will be lower than required. This is due to the reduced voltage caused by the excess resistance. This is one of the most compelling reasons to use an oscilloscope for any diagnosis on a PWM controlled circuit. Pulse width refers to the exact time the control is pulled high or low. This is measured in milliseconds. A circuit that uses a high side driver requires us to measure the pulse width when the voltage is pulled high. On the oscilloscope, we have a cycle of 1 second, so our pulse width is 750 milliseconds. If this circuit was controlled by a low side driver, the pulse width would be 250 milliseconds. Now that we understand duty cycle and pulse width, let's look at frequency measurements. Frequency is determined by how many times an event cycle occurs in 1 second. Frequencies measured in hertz. This output is pulled high and low 50 times a second. This equates to 50 complete cycles a second, or 50 hertz. Let's look at some uses for PWM control in a motor vehicle. Some lighting circuits use PWM control to change between brake and tail lights. This tail stop lamp circuit only has one supply from the body control module. By changing the duty cycle, we can change the light intensity to reflect the vehicle needs. With a duty cycle of around 25%, the light is only as bright as a 5-watt bulb. When we apply the brake pedal, the BCM will increase the duty cycle to 100%. The lamp now has full current flow and emits the full 21 watts. This is a great and cost-effective way to control lighting. But it's not just the duty cycle that does this. The frequency of the control plays a major role in what we see. We have close to 15% duty cycle at our lamp and it's dull, but it appears to blink. This is because the frequency is too low. In this instance, it's around 28 Hz. By increasing the frequency, but keeping the duty cycle the same, we can eliminate the blinking effect. Our current draw, and therefore the lamp output, remains the same. Permanent magnet type, electric motor speed and direction can be controlled with PWM as well. We've seen this in throttle valves, servo motors and fuel pumps. An electric motor's speed can be altered by changing the duty cycle control. This is the effect of increasing or decreasing current flow to the motor. So a small duty cycle equals low current flow and therefore low motor speed. With the use of bidirectional drivers in a control module, the current path can be reversed. This will change the motor direction. When looking at this on an oscilloscope, we can see the PWM control changing the duty cycle, so the motor speed changes. But if you look at the supply voltage, it remains constant. It will be either 0 or 4 volts. This time, I'll use the multimeter to monitor the voltage. We'll see the voltage increase and decrease with the motor speed. The reason for this is because the multimeter cannot react fast enough to the change in the duty cycle control. It displays an average voltage reading that we can see. This is another important reason to only use an oscilloscope when diagnosing one of these systems. The multimeter can be very misleading. This motor is supposed to be driven by a 50% 5-volt duty cycle. A multimeter would display approximately 2.5 volts. As you can see, the meter is showing 2.5 volts. Let's have a look with the oscilloscope. The pattern shows that this is not a PWM control, but a steady 2.5 volts. From the multimeter reading, it could be assumed that the fault was in the motor. This would be incorrect. The actual fault is a short to voltage. The oscilloscope told the whole story. By now, you're probably thinking that this PWM control is just brilliant, but there are some downsides. If the duty cycle control is too low for a motor to turn, a high-pitched squeal will be emitted. This is due to the low current flow and the high frequency of the control pulses. We can hear this in a throttle valve motor. As the valve is moved, the sound will change. PWM may also be used as an input to a control module. It can be used as a position or a speed signal, or even as a humidity sensor input. This multifunction airflow sensor sends a varying PWM and frequency signal to the engine control module to determine the temperature and humidity of the air entering the engine. By changing the temperature, the frequency will shift. A change in humidity will cause the duty cycle to change. By now, you should have a reasonable understanding of pulse width modulation, duty cycle, pulse width, and frequency used as inputs and outputs to and from a control module. If there's any part of this video you're unsure of, please review it again, as effective diagnosis can only happen when you have a sound understanding of the system's operation. Thanks for watching.